Today, we're diving into a kind of AI that's inspired by, well, the most complex and efficient computer we know of, the human brain. It's a fascinating story about pulse, pattern, and what might just be the next wave of computation. So let's just start with that one massive question. What if we could build an AI that doesn't just crunch numbers, but actually communicates, learns, and operates with the same incredible efficiency as our own minds? That question right there is driving a truly revolutionary shift in artificial intelligence. And to really get what this shift is all about, we've got to look beyond the kind of AI we hear about every day. We're stepping into a whole new territory, one that's deeply inspired by biology, to try and build a smarter, more efficient kind of neural network. And at the absolute heart of all this is something called the spiking neural network, or SNN. The two key ideas here are mimics and spikes. See, instead of just abstractly modeling how a neuron works, SNN try to copy the actual way our brain cells talk to each other, using these sharp, distinct little electrical pulses. This is a really great way to picture it. Think of most AI today as constantly shouting a stream of numbers. They're always on, always processing data. But spiking networks, they're more like a sophisticated conversation. They communicate in a precise rhythm, sending out a pulse only when something important actually happens. It's a completely different philosophy of computation.
Okay, so if these networks are communicating in rhythm, what does that language of spikes actually look like? I mean, how do you turn simple little pulses into complex, meaningful information?
Well, the process is actually elegantly simple, a lot like a real neuron. First, the neuron collects some input. As it does, its internal energy level starts to rise. And when that energy crosses a specific line, spike. It fires off a single, clean pulse of information. The most important thing to get here is that it's event-driven. The neuron isn't just humming along constantly. It's waiting for something meaningful to happen before it acts. And this is where SNNs really get their superpowers. First, as we just saw, they're event-driven, which makes them incredibly energy efficient. Second, they use what's called temporal coding. This means the timing of the spikes is everything. It's not just that a neuron fired, but precisely when it fired that carries the information. And third, they have synaptic plasticity, which is just a fancy way of saying they learn on the fly. Connections get stronger or weaker based on activity, literally rewiring the network as it learns, just like our brains. So we have this incredibly efficient, brain-like way to process information. Cool. But why does this really change everything? Well, this leads us to a whole new field of computing, a true revolution in how we design our machines. It all boils down to one single, massive advantage: energy efficiency. Today's big AI models drink power like there's no tomorrow. But because SNNs only compute when they have to, they open the door to a future where powerful AI can run on just a tiny fraction of the energy. We're talking about running on a small battery. And this whole idea of efficiency is really the heart of a bigger field called neuromorphic computing. If SNNs are the brain-inspired software, then neuromorphic chips are the brain-inspired hardware. The goal here is to build computer systems from the ground up that basically think and operate like a biological brain. And when you put that software and hardware together, the potential applications are just stunning. Imagine robots that can adapt in real time without needing a constant connection to the cloud. Or smart sensors in your phone that can do complex tasks without killing your battery. We're even talking about brain-machine interfaces that could let people control prosthetics just by thinking. It's really incredible stuff. Now, it's a beautiful vision for sure, but let's be real, we're not quite there yet. Like with any cutting-edge tech, there are some pretty significant hurdles that researchers are working hard to clear right now. So let's break down the main challenges. First, just training these networks is really tricky. Standard AI learns through tiny adjustments, but the all-or-nothing spike makes that hard. Second, to get the most out of them, you need special hardware, like Intel's low-heat chip, and that hardware is still pretty experimental. And finally, there's scalability. Building SNNs that are as massive as today's biggest deep learning models, well, that's the next big mountain to climb. But hey, challenges are just problems waiting to be solved, right? And despite those hurdles, the path forward is actually becoming clearer. So let's wrap this up by taking a little glimpse into what the future of this neuromorphic tech might really look like. If we look ahead maybe a couple of decades, some researchers are predicting that by 2050, this technology could be mainstream. Picture this. You've got the SNN software running on specialized neuromorphic chips that use components called memristors to act like perfect artificial synapses. That combination could kick off an era of truly intelligent, incredibly low-power devices. And this quote really just says it all. This isn't just about building a faster calculator. It's a real, fundamental attempt to bridge the gap between biology and technology, to literally replicate the language of the brain in silicon. Which leaves us with one final, pretty profound thought to chew on. As we get better and better at copying the brain's pulse and its pattern, are we just building a more efficient machine, or are we actually laying down the blueprint for a totally new kind of mind? That's definitely a question worth thinking about. Thanks for joining us.